Okay, we're going to talk about optimization. This is a really big topic. It's one that students, I find a lot of Calc 1 students will struggle with it because it's really involved. There's a lot going on in this. But really at its core, it's just an application problem. So we're going to talk about the basic overview here. We're going to find absolute extrema in context. So there's going to be some sort of specific application that we're going to be looking for absolute maximums or absolute minimums for. The big thing that students will struggle with is how do you set up problems. These are a lot of times going to be like word problem type things. Like I said, you're going to be in some sort of context and you're going to be trying to figure out how to deal with things. So we'll talk about setup, try and give you some hints on some keys or maybe at least a checklist of things that we'll need there. A lot of this is going to be about finding absolute extrema, and so we'll recap that, but the main thing that students will struggle with is the setup. And then we will do a small example. I'm not going to do a bunch of examples in this video for a couple of reasons. First, that can get really long because some of these examples are pretty involved. And also, there are tons of resources of other people doing videos of optimization examples. So I'm going to try and link those on Canvas so you can see those. I'll also maybe write up some kind of helpful guidelines on setting up some specific homework problems so that you don't have to struggle through that as much, or at least I can give you some hints on some of that. So anyways, let's get this going. We're going to talk about optimization. First, a basic overview. Like I said, this is finding absolute extrema in context. So this is super applicable to a lot of different contexts. This might be the most applicable topic from Calc 1. It might be the thing that you're most likely to see in whatever field you end up with. The whole point is that we want to give some sort of an optimal solution to some problem, given a set of parameters and bounds and things like that. So here's some examples. Maybe we're trying to find a way to maximize the profit under some restraints that we have about costs and manufacturing abilities and stuff like that. Or maybe we're trying to manufacture some object and we have a fixed amount of material to create it. So we have some sort of fixed surface area and we want to maximize the volume of it. Maybe we're trying to create some sort of a box or something like that that holds the most space. We can fit the most stuff in it, but we have some fixed amount of material to do it. Or maybe we're trying to minimize the time that it's going to take to perform a certain type of task under some working conditions. So we have some sort of a setup that tells us what our options are at least, and then we'll try and find some sort of a mixture of those options to minimize the time that it takes. So hopefully you can see really quickly that with just even these three really basic examples, these are things that show up in manufacturing, in business, in management, or anything like that. So you end up seeing these kinds of optimization problems lying underneath the surface in tons of different areas. So the main key that we're going to have to struggle with is how do we set these problems up? These are going to be word problems, or if you're in like a real life situation, it's just some sort of a specific case situation that you're living in or sitting in with work, and you've got to sift through all the different pieces that are involved and try and collect as much information as you can. And we're going to try and continually just translate it into some sort of a calculus context. I'm going to talk about a calculus statement later on that I want to include on every optimization problem, because I think once we have that, things get really easy because we're used to doing calculus, or at least easier. So here's a kind of guideline of some of the things that we want to do. We want to go through our word problems and just try and name all the relevant variables and parameters. Call them X or Y or H or T or whatever. Maybe give them relevant names. If you're looking at some sort of a height, it might make sense to call it H. If you're looking at some sort of a time variable, it might make sense to call it T. And we're going to just try and name every little piece that we have involved. Then we're going to try and find some of the conditions and boundaries on those variables. So like, what are some reasonable expectations for this height parameter? Well, maybe height can't be negative in this context. Maybe it doesn't make sense to have a negative height. And maybe we also have some sort of a maximum height that makes sense. And so we're going to end up kind of coming up with like intervals that are almost like domains, you can think. They're just intervals of reasonable values. If we said something like height can't be negative, maybe we just have something like height is greater than or equal to 0. Maybe it doesn't make sense to have a 0 height, and so we just say height is greater than the 0. And we're going to come up with bounds like this on all of our variables that we have. Then what we're going to do is try and come up with ways that they relate to each other. That's only going to be the case when there is some sort of a natural relationship to each other. Maybe we have something like a distance and a time and a speed, and we know there's a relationship there. We know that speed is equal to distance over time. And so maybe we have these kind of natural relationships. Or maybe we're just told, hey, you can't have somebody, or maybe we'll say like you can't have more than 3 people working on this specific task at a time. And so we have this kind of a connection that says like, okay, we can have like a time that one person spends and a time that another person spends and a time that another person spends, but after that we can't. And so a total time might be a sum of 3 people's time. I don't know, whatever. In a lot of places, these are called constraints. And so if you're watching other videos, they most likely will refer to this as a constraint. It's just a relationship between variables. And then eventually we're going to have to come up with a thing that we're trying to optimize. This is essentially the function that we're going to work with. So maybe we're looking at some sort of a volume function. We have to come up with the relationships between all of the parameters of whatever shape that we're working with. If it's a box, like a rectangular box, we might have like a length, width, and a height. And so we'll put all those things together and come up with a volume function. Volume is length times width times height. Our goal is that we're going to try and make that function a function of a single variable. So we're used to dealing with things like f of x, v of, I don't know, h, we'll say. Maybe we'll say p of t. This is like maybe a profit with regard to time. I don't know. Something like this. The problem here is that we're going to have to shrink everything down to only being in terms of one variable. That's where these constraints are going to come into play, these relationships between variables. We're going to have to try and write things all in terms of one variable. Once we have all these things, some boundaries on variables, connections between them, and we can create a function, we should be able to come up with this calculus statement that we're going to really care about. We want to be able to find absolute maximums or minimums. That's going to be depending on the context, whatever we're told, of some function of a single variable, and we're going to want an interval, almost like a domain of that function. What's reasonable for the inputs? Now that's going to change based on what your input variable is, right? That's going to be just the reasonable values for that input variable x. So you can think of this as like a domain. Once we have this calculus statement, things should be pretty easy because we're going to have a function on an interval and we want to find absolute extrema. And so after that, our big question is just a recap question. Remember, let's figure out how do we find absolute extrema. Well, there's a couple of different ways that we can do it that we've already talked about in this class. The first is if we have a continuous function on a closed interval, then the extreme value theorem kicks in. And remember, the extreme value theorem, oops, that's spelled wrong. There we go. The extreme value theorem says we're guaranteed that both extrema exist. There is both a maximum and a minimum here. That means a solution to our problem is there somewhere. We just have to find it. And then remember that little lemma that we had, that was like the add-on to the extreme value theorem that I normally just include in the extreme value theorem, says, well, we know where they're going to exist. They're either going to be at the endpoints of the closed interval or at critical points in the interval. And so to find these absolute maxes or mins, whatever we're looking for, we just have to find all the critical points and all the ending points, and we make a little table like this. Find all these x values, plug them into the y values, and we'll just say what's the biggest y value. Or maybe, if we're looking for a minimum, we'll say what's the smallest y value. And then we'll interpret things from there. And so if we have a closed interval, that ends up being really nice because we can use this little extreme value theorem and its connected little lemma. Sometimes we'll have some options on whether it makes sense to have a closed interval or not. And in my case, if it's even reasonable to have a closed interval, I'm going to do it because the extreme value theorem is pretty easy to work with. Now, what happens if you just have a continuous function on some interval? We don't necessarily know if it's closed or not, or maybe one endpoint is closed and one is open. I don't know, whatever. Then we have to hope that there's only one local max or min. There's only one local extrema. In a lot of cases when this happens, we're really only going to have one critical point, although it's possible that we have more than one, but only one of them can be a local max or min. So if we really just have that one critical point or one local extrema, then we know that whether it was a local maximum or local minimum, it was going to be the absolute version of that. So we have this single point of interest, and it's going to be the absolute max or min, depending on which one it is locally. So to find those, we know that those show up at critical points. So we'll go ahead and find all the critical points in the interval, and then we have to figure out if they're local maximums or minimums. And we've got two ways of doing that. The first derivative test, that's that sign chart, where we see, okay, does our function increase up and then decrease down where there's a maximum there? Or the second derivative, remember, this is the second derivative evaluated at the critical point, and if it was negative, then we'd say, all right, concave down. And remember, this only works for horizontal tangent lines. And so we have a max here as well. So we'll do either one of these things to check. And it's kind of up to you. In some cases, it'll make a lot of sense to do the second derivative test because it might be really easy to find the second derivative and evaluate it. If the second derivative is really hard to get, maybe it's best to just do the first derivative test. So you've got some options here. If you have a continuous function on a closed interval and there only is one critical point, then you can do any of these three options. You can do the extreme value theorem, check the ending points and the critical point, do the first derivative test, see if you do get a local max, and then it's the absolute max, or do the second derivative test. The problem with doing the first or second derivative test in both of the cases that I've drawn up here is, what if we were trying to find the minimum? Well, that's a little bit harder, right? Because maybe the minimum was showing up at an ending point, and if we didn't do that extreme value theorem where we check the ending points, things can get hairy. So just be careful. Make sure that we actually do check our critical points here. Make sure that they are what we think they are. And that should go pretty well. All right, let's end this video with a small example. Now, I put small in quotes because while this is a small example, it's not going to be a super easy one. This is still something that's pretty involved, and things are only going to get bigger from here. But as you do more and more of these, you're going to get better and better at understanding how to kind of sift through all the information and get the important parts. So here we go. Very small setup. Find the maximum area of a square that fits between the parabola y equals 9 minus x squared and the x-axis. So we're going to be looking at a square here, which maybe actually I want to change. I want rectangle. I'll change that on your notes so that the version that you're seeing that's blank will have it written rectangle there. I don't necessarily want both the side lengths to be the same, so that was just a mistype. So we're going to find the maximum area of some rectangle that fits under this parabola. Let me draw a picture of the parabola here, and then we'll see what's going on. So we've got a y-intercept up here at 9, and we've got x-intercepts down here at -3 and 3, and here's our parabola. Going down like that. Down like that. That's not a very good picture, but oh well. And we're going to pick some rectangle that looks like this. We're going to try and draw the biggest rectangle that we can in terms of area. So maximize the area of this rectangle. You'll notice that the boundaries are going to be this x-axis on the bottom and the parabola on the top. Cool. So what we need to do is come up with ways of defining some variables here and then connecting those things together. Now, we're going to have some sort of a width and a height of our rectangle. And we know that the area is going to be the width times the height. So first, we need a way to define the width. You could call this W if you want. And you could call the height h. Maybe that makes sense. But we'll also notice that based on this graph, it might make sense to call this width something specific. Notice that if we put a point right here, this point is some x and y value. And if we put the same point over here, we have this nice symmetry for our parabola. And so it's just the same x value but negative, and then the same y value, meaning the total width is 2x. And then we'll notice that the height is just y. So really, we have 2x times y. Now, this is an important part where we have to start looking at a constraint. We have this constraint here, this connection between the variables. This is the thing that defines how x and y are connected to each other. Now, this one is a nice, easy one because we're just told explicitly what that is. We said y equals 9 minus x squared. Sometimes that constraint will be a little bit more implied. Maybe it'll be written in words, and so we'll have to translate that to some math notation. Maybe it'll be something like, oh, the sum of these two things is at most, 50. And so you'll say, oh, okay, there's two variables added together that are going to equal 50. That's like x plus y equals 50 or something like that. But that can be a little bit trickier. So now what we'll say is that we have an area function that's 2x times 9 minus x squared. Now, we still need some kind of bounds on these things here. So we have to think, okay, what are the boundaries of our x values? Notice I don't really care about the boundaries of the y values. I can think about those, but since my function is written in terms of x, it doesn't really matter. Now, we could go ahead and solve this for x and have it written in terms of y, and then plug that into this value here, and then we have an area function of y. And then we care about the boundaries on y. So what I'm going to look at is, say, x here, we need a biggest value and a smallest value. The biggest value, you'll notice, the farthest out we can go is right to here, and that's at 3. And the smallest value you might think is negative 3, but actually, remember, x is just this half. So the smallest value is 0. So we have some interval that we could go ahead and say, all right, 0 to 3. But what I'm going to do is close my interval, because now I can say, okay, sure, if x was 3, then my y value is 0, right? If that's this point here, and so my area is 0. So that doesn't even make really sense. And similarly, if x was 0, then my y value is 9, and I have some rectangle that's got 0 width, and that doesn't really make sense. But I'm going to use a closed interval here so that we can use the extreme value theorem. We have got a continuous function on a closed interval. So this is our setup. Some parameters or variables that we defined over here. We used the constraint and our context to build some sort of a function, and then we have a domain for that function. So we can write out our calculus statement now. What we want to do is we want to maximize this function on this interval. So here's our calculus statement. Now I went ahead and, oh shoot, another typo. This is supposed to be 18. There we go. I went ahead and multiplied this out. So it's really 18x minus 2x cubed here. That's going to make it a little easier to work with. And we want to maximize this thing. Now, this part should be easy, or at least easier. If we're familiar with finding absolute extreme, and we can say, great, continuous function on a closed interval, let's use the extreme value theorem. I'm going to go ahead and find a derivative. My derivative is 18 minus 6x squared. I need to find critical points. I'm going to set this derivative equal to 0. Notice that it's going to exist everywhere. I can't ever have any x values that will make it not exist. So I'm going to say 6x squared equals 18. So x squared equals 3. So x is plus or minus root 3. That's an ugly x. Let me fix that one. There we go. Cool. Now, only one of these is a critical point, right? This is my interval right here. So my critical point is really root 3. And now I can use the extreme value theorem. I guess this part isn't really the extreme value theorem yet. I can use the extreme value theorem to say my ending points were 0 and 3. My critical point was root 3. I can plug all three of these values into my area function to get the y value, the output. Now, I shouldn't really say y value here, because y means something else in this context, but the output of the area function, the thing that we care about. Maybe I'll write that. Okay, so if you put 0 in here, we get an area of 0, right? 0 times 9. If you put 3 in here, you get 6 times 0. And if you put root 3 in here, you get 2 root 3 times 9 minus 3, which is 6. So I'll just call that 12 root 3. And it is easy to see, even if we don't know what that is, that this is the maximum. Now, we were told to find the maximum area, and so that's what it is. It's 12 root 3 units squared. If you wanted, we could also have done the first derivative test, and we could do a little sign chart. We could say, maybe I'll do it a little bit more clearly. We could do a little sign chart, and we could say from 0 up to root 3 up to 3. And we could check the sign of the derivative here in between. And we could notice that it's positive and then negative, which means our function goes up and down. So there's a max. Since there's only one of these things, it's the absolute version of it. You could also have done the second derivative test, which might be actually pretty easy to do here, because the second derivative is just negative 12x. And so if you evaluate the second derivative at root 3, that's negative 12 root 3, which is negative, meaning your function's concave down, max. So extreme value theorem, first derivative test, second derivative test, they all give us the same answer. There's a maximum at this point. But notice that the extreme value theorem right away gives you the output of the area function. In both of these other cases with the first and second derivative test, we'd have to go back to that area function, plug in root 3, and get 12 root 3 as that maximum area. So, our conclusion. Maybe I'll type this. No, I'll just write it. The maximum area is 12 root 3. And if we cared about the dimensions, we've got them. The dimensions are root 3 for one of the side lengths, right? That was right here. And then we need the other dimension. We have it right here. Y equals 9 minus root 3 squared. So that was 6. So that's the size of our rectangle. It's root 3 by 6, and it's got an area of 12 root 3. Cool. So that's what we've got for optimization. This is a small problem that still seems a little convoluted. Go through a bunch of the other examples that I'm going to link, and you'll see lots of different ways of building these things, and it's all going to be dependent on context. Hopefully that's helpful. Good luck, everybody.